In this lecture, I'm going to work through some example problems from chapter 5 that deals with calculating the center of gravity and centroids of objects, and chapter 6, especially from the part involving frames and machines. And this is based on the request from some of you for some more example problems. So in the first part, I'll talk about 3D shapes and solve two problems there after reviewing some of the necessary background, and then end with two problems, one from frames and one from machines. So let's first go back and review how one calculates in general the center of gravity of an object, right? And we will talk about 3D objects, and this discussion is absolutely valid for a 2D object as well. So the question here is that I have this object which has a weight W, and I want to find out where its center of gravity is. So that's the question. So how does one go about doing this? If you remember, what we did in the 2D case was that we find the moment of the weight, right? So that is, remember, weight is the force due to gravity, and we are applying equilibrium of the moments, and from that, when we calculate the moment of the weight about each of the for each of the dimensions or the coordinates x, y, and z, then you would have basically solved for the 3D case. If it was 2D, you would either have a pair, like either xy or xz or yz, for you to be able to calculate. So now what we have here is that we are given the origin O for this coordinate system, and we want to find out with respect to this origin where the center of gravity of this body is. So what we need to be doing here is finding the first moments, or the moment as given by this equation here. So remember, xw is the first moment, and also x is your center of gravity, in this case x bar, right? So this quantity here, w is of course your weight. So you can see either you have an integral or a summation over over the weight elements throughout the entire body, and once you carry out either the summation or the integral, you can then find out where the centroid is, or the center of gravity is in this case, right? Similarly for the y center of gravity and the z center of gravity. So this is in a sense what we need to do. And in general, if you have a complex shape like this, we are of course going to be using an integral. If you have simple shapes, you might be just able to directly apply the known forms of the first moments in order to find where the center of gravity is for the x, y, and z. Now, the center of gravity of course involves the weight. What we have also talked about is the centroid, and the centroid is a similar concept to that of the center of gravity, and it comes about by looking at a body which is homogeneous, right? That means throughout the body you have uniform density, and in that case I can write down my weight as being given by this product of gamma times v, where gamma is the specific density called rho g, right? And v is the volume. So now the question is, how do we go from center of gravity to finding the centroid of this object? And the response is similar to what we did in the previous slide, right? Just like in the 2D case, we write down the first moments for each of the coordinates, but now I'm going to replace the w by gamma times v, and you can see now throughout that the gamma just cancels out because it's a constant, and what I'm left with is basically the definition of the first moment to calculate the centroids. So the centroid here is x bar. It's going to be the integral of x dv over v, right? And so on and so forth. So this is really what we're going to be using for the two problems that we're going to solve. Okay, Now the two problems I'm going to solve, one which is your home assignment problem number 1, as well as another example. I'm just going to basically use the information that we have here for common shapes, right? For example, one of the problems involves a cone, another one involves a pyramid, and so we will be using these forms here that tell us where the centroid is, as well as the volume. So this is the volume and this is the centroid. So depending on what axis it's oriented around, it may be the x bar, the y bar, or the z bar, right? And so we're going to use this information. So here's the first problem. Pause the video here, take a moment to read through the problem, and then come back and attempt it based on knowing the value of the centroid for the various known shapes. So we have a cone and we have a cylinder, and what we want to do here is to determine the location of the centroid of the composite body. So as you can see here, an axis has not been specified. So the way we can go about doing it is that we can lay out an axis, and if we are if we are smart, we are going to say, let's lay out an axis that utilizes the symmetry of the body. So you can see that since it's a cylinder and a cone, there is an axis of symmetry passing through the tip right here, right? So I can I place my origin right here maybe. So I'm going to say this is x, this is y, and this is z, right? So that's one way to do it, but I believe the solution here that I have actually uses y along this axis here. So let me do it this way. So I'm going to do this. So this is x, this is y, and this is z. So now you see immediately that my x centroid is 0 because it's right at the origin, because if you look at this object, it's symmetric about the x-axis, right? Similarly, my z centroid is 0 for the same reason. So what we're left with is we basically want to calculate the y centroid value. So let's go about doing that. Now so this is what we just said, so x and y, right? So let's see how we can calculate the y bar so that we have all three coordinates for the centroids. Now this thing recognizes that this is a composite object. We have two different basic shapes here. This is a cylinder, right? And below that is the cone. So this is the cone here. So what we can do is we can refer back to that table or the figure that shows us the various centroid values for different shapes, or you can actually do it through an integral form. Of course, that's much more difficult here because we need to do two different integrals, and so we'll just use the idea of the composite and begin by creating the table. So what do you do to create the table? Well, you take the part and identify all the parts that you have. So we have a cylinder and we have a cone. You write down its volume, and then you write down its y bar, the centroid of the individual shape, based on either looking at the table where you have the individual shapes or by calculating the integral, right? So you've written down that. So if you look at the cylinder, our volume is pi a square h, right? So pi a square is the area and h is the height, so that gives you the volume. Similarly, if you look at my cone, my volume is 1/3 pi a square h, and then I know that the centroid of the cylinder is basically at half the height of the cylinder. So I'm going to take h and add half to it, and I'm going to end up with 3/2h, right? And for the cone, if I look at the table or the figure with the known centroid values of different shapes, I find that it is 3/4h. So I'm going to use that here. Okay, so now you have all the information. So remember, we are going to apply this this integral here, or the summation form here. So I now calculate the product y times v, and so I have these two. And so I have now broken this up into two sums. One is the sum for the cylinder and the other is the sum for the cone, right? So basically I have yv of cylinder plus now yv of cone, and that quantity is the result here in this summation column. So the final step now is that I take the fact that my y centroid is going to be this summation here of yv divided by the total volume, which is this quantity here. And so when we do that, you get something like this. So you'll end up, when you do the analysis carefully, you'll see that your y bar is 21 by 16 h. So that means, given that this is my origin here and this is my y-axis, I need to go about 21 by 16 h in order to find the centroid of this object. Okay, so hopefully this is this problem is something that you will be comfortable doing. Okay, let's move to the next one, and this is one of the assignment problems. And again, we have a composite body. In this case, we have two known shapes. Again, one is a rectangular prism and the other is a pyramid. So here's your rectangular prism, and the pyramid is shown here, right? And so what we want to do is determine the location of the x centroid when h is L by 2. So we are already given the axis here, so x, y, and z, and so we want to find the location along the x centroid. So I'm going to use the same approach as we did in the last one, where we will create a table with the various required quantities. So remember, the table had, the part, and then we had the volume of the part, and then in this case we're going to write down the x centroid, then finally calculate the sum by taking the product of x times v, and then doing the sigma down here, right? And so that's really what we're going to do. And I'm going to use the fact that we have known shapes, and I look at the table now, and so here's our table. Here we have the rectangular prism, we have the pyramid. So for the rectangular prism, the volume is nothing but, it's a slab, so it's just L times A times B, the dimensions. The position, because of symmetry, is going to be half times the length along the x-axis, so that's what we have, and we have x bar v. The pyramid is of course a little more complex, so doing the integral is also much more challenging. So the good news is that we can just look up the table, and we recognize the volume, and the fact that its centroid is 1/4 of the height from the base, and so our centroid position here is L, which is the length that the pyramid is shifted from the origin to, and added, and we add the quarter h to it, right? So again, we are remember, we are applying this idea here that x bar v is going to be sigma of xv. So these are the summation for each of the shapes, and that's what we have right here. And so my x bar is just going to be my centroid x bar is going to be sigma xv divided by the volume, or the sigma of the volume of individual units, right? So we can, here is the summation index. Okay, and that's what we have right here. So this is the centroid calculated for x bar. So hopefully this also is something that you will be able to do, since we are using simple shapes. Okay, let's move on to two examples from our recently concluded topic of frames and machines, and we'll begin with this first one here. You can again read through the problem, pause the video, attempt it, and then you can come back and look through the solution, right? So the question asks us to find the force in member BD as well as the components of the reaction at C. So if you remember, the steps in solving for frames and machines is that step 1, you create the free body of the entire frame, and in step 2 you dismantle the frame and then find out what's missing. So why is this a frame, first of all? So if you look at member AC, it has 3 forces, right? So it's not a 2-force member anymore, and that means you have a frame. And where are the 3 forces here? There's force applied at A, applied at C, and applied at B. Okay. Now the interesting thing here is, if you look at member BD, this is actually a 2-force member, right? So the forces here are just basically going to act something like this. So it's a 2-force member, and so it turns out that a shortcut route to solving this problem is that I just dismantle AC and I look at it. So I'm just going to look at AC here. Okay, So A is 90 pounds, so that's A right here. I have B, and the reason I can do this is I know exactly in what direction the force FBD is acting, and that's along the two force member BD, so that is now well set. And then I have C here, since it's a pin joint. I have both a CX component and a CY component. So that is my free body of the dismantled member AC. And you can see here that if I look at this, I have unknowns here and here, and I have a known quantity here, which is 90 pounds. So immediately, if I want to calculate the unknown FBD, I just need to take moment about point C, which eliminates the two unknowns CX and CY, and thereby I can just calculate what FBD in terms of what A is, right? The force at A is. And so that's how we are going to progress through this problem. So we can, as I said, we can just directly dismantle and analyze the member. And the reason I want to re-emphasize is that because we know that BD is a two-force member, so we know the direction of the force that's acting on it. Unlike normal three-force members, where the force at one of the locations is both unknown in magnitude and direction, in this case, it turns out that because BD is a two-force member, we know the direction and magnitude of the force, so we can directly go and dismantle this frame and look at AC, right? And so this is what our free body diagram looks like. These are the dimensions of the sides of the triangle that help us calculate the angle. You can work through this from the fact that we're given that this is 4.5 inches here, it's 7 inches here, and 6 inches here. And so once you work through that, as I said, take the moment about C. We have two components about C. So one is due to the force acting here, A, and the other is due to the horizontal component of force FBD, and that is given by 4/5 FBD. And so that leads us to the solution that FBD is 300 pounds. So now finally we're left with CX and CY, and you can do two ways. Either you can we can start by saying that if I look at sigma Fy as the equilibrium in the y direction, we know that's 0, and so that is given by the component of Cy being equal to the vertical component of FBD, which is pointing in this direction, and so that gives us 180 points. And finally we are left with Cx. So what do we need to do here? Well, you can see here that the force A and the force Cx are actually trying to rotate this member about, right? So the way to get equilibrium is to find the moment to find the moment about B, so that this object is in equilibrium, and when you do that, you can actually get to Cx. And that's because now we have known quantities here, and the only missing quantity was Cx. So that's one way to do it. Okay. The last example, this is a very quick one, is basically related to this machine here, where you have a hydraulic cylinder that is helping you do some mechanical work here, right? So for example, you can pull down here and it's going to extend the cylinder and do some kind of work. So read through the problem, pause the video, read through the problem, and all we need to do here is draw the free body diagram that can be used to determine the force exerted by the hydraulic cylinder on pin C, as well as the reaction at B. Now again, this is interesting because if you see CD is a two-force member, so we know exactly the direction of the force that is acting at C due to this cylinder CD. So very simply, our free body diagram boils down to this. B is a two-force is a fixed joint, so I have two components for the force at B along X and along Y, and of course I have this load applied here at point A and finally at point C. And again, based on the dimensions that we have here, we can actually calculate the angle that we need here in order to do the final analysis. Okay, So that is another piece of information you will need when you actually solve this problem. But our problem here just required us to draw the free body diagram, and that's what this is. Okay, so hopefully you have more examples in front of you to build your confidence working through problems, both for the 3D center of gravity and centroid calculations, as well as frames in machines. Thank you.